Okay, we're going to be talking about the match pairs t-test. All right, so we're still doing hypothesis testing. This is the last t-test actually that we're going to be looking at how to run. And just so you can get ready for the video, now would be a good time to go ahead, go to the course calendar. Down here on week 12 is the notebook 16 matched pairs t-test, and that is the notebook we're going to be running today. Okay, so what is matched pairs? Well, matched pairs means that we have two samples and that the participants or the research subjects in those samples must be matched in a very specific way. And the most common way is pretest versus post-test. You have the same subjects take a pretest, there's a training module, and then you give a post-test. Okay, and in this setup, we actually calculate a gain score, which is fairly obvious. If you think about it, the gain score is equal to post minus pre. And I'm sorry that I'm struggle bussing a little bit trying to write with the mouse. But post minus pre is how we calculate a gain score. And if you think about it, if you made an 80% on the math quiz and then had the training and then you made a 95, you do post minus pre, that's 95 minus 80. So that's an increase of 15. So the gain score just tells me how much I gained from from pre to post. Okay. Um, there are other ways to match the samples. For example, a lot of times when they're looking for um, different causes of certain diseases or things like that, they do twin studies to see if they can find a link. They often will ask things about from both partners in a marriage, and they'll match the samples that way. You'll also see these go no go reaction time tests, and they'll do dominant hand versus non-dominant hand. So these are all there are a lot of different ways to pair these samples, but the idea is that the same person or partnership is represented in both samples. And when we do that, we do need to do a different t-test. You will get a different result doing match pairs t-test versus the two sample t-test that we talked about earlier. Okay, so in the first example that we have, we're talking about violent crime rates in Georgia and Alabama. Okay, so if you haven't paused yet and gotten notebook 16 open, now is a good time, and make sure that you initialize that first code block. And then it's kind of interesting because the very first thing they do is they show us this graph. And the dark blue is Georgia and the yellow is Alabama. And do we see any relationships in this data visualization? So we don't know anything about this question except what we see in the data visualization. And I hope you're thinking, well, normally I root for Georgia to win against Alabama, like in football games. Didn't think we wanted to win this particular one because these are murder rates, and it appears that a lot of the time the blue is higher than the yellow. So the hypothesis is going to be that Georgia has higher murder rates than Alabama. And here they show us another visualization. They show us the difference. And notice that this is Georgia minus Alabama. So Georgia minus Alabama is going to be negative when Georgia has a higher rate than Alabama, and it's going to be positive. I'm sorry, let me say that again. Georgia minus Alabama is going to be positive when Georgia is larger, and it's going to be negative when Georgia minus Alabama is going to be negative when Alabama is higher. Okay, so they run the test, and I'm going to jump back to the PowerPoint slide just to show you though what is going on. Okay, so they're grabbing the scipy.stats and it is t-test underscore rel. That is the dependent samples, the match pairs t-test. It had just, I tell the computer _rel. Now notice that we had the Georgia rates and we're doing a dot column. So we're getting the murder rates as an array and putting in the first array here. And we're putting in the second array here. Okay, I also want to point out a couple of things with the Georgia. Notice that the GA is sorted by year and the Alabama is sorted by year. Why? Well, this is matched pairs. And so to make sure that we're matching the correct year, we're not comparing 1960s Georgia to 1980s Alabama, right? We want to be comparing year by year. So when we sort by year, that gets us the nice matched pairs sequence that we need in both arrays. And now notice that we are taking an array. So we're putting the Georgia array in first and the Alabama array in second. So we're checking to see, and sadly, I don't want to run this hypothesis this way. Why? Well, I'm not a Georgia native, but I've been here for 20 years, and I don't want the murder rates in Georgia to be higher than in Alabama. But this is what we're checking. Why? Well, because of the data visualization. The data visualization shows that there appears to be a relationship, and the relationship is that Georgia appears to be higher. So we're going to check the relationship that Georgia is in fact higher. And notice that when we run the test right here, you can see the test statistic is 1.865 and the p-value is 0.0689. Okay, so there's the t-value and the t-statistic and the p-value. And I want to make something really clear right now. This is a two-tailed p-value, and we don't want a two-tailed p-value. We have a directional test. We have a one-tailed test. Okay, so we want to actually take this number and divide by 2. Why? So we get a one-tailed t-test, right? The p-values from the one-tailed test are exactly half of the p-value from the two-tailed tests. Okay, so if we want that number divided by 2, I'm sorry, let me get back in there. Okay, and you see what I did here. I just copy pasted this p-value, right? I just copy pasted that number in here, divided by 2. Why? Well, you'll see that the report, so I don't think you'll have this cell in your book, your notebook. The notebook kind of does divide by 2, but doesn't really say why. Okay, and the book has the same conclusion that I do. I said P is less than alpha. Now, 0.0668 is not less than 0.05, but again, we divide this in half and it's 0.034, right? So the one-tailed p-test is P equals 0.034, which is indeed less than 0.05. So we reject the null, and that indicates that for the time period covered, maybe not all of our history, but from 1960 to about 2005, the murder rates were higher on average in Georgia than in Alabama. That's our conclusion. The second example we're going to do is actually a pretest versus post-test design. In 1972, the Supreme Court banned all death penalty, banned the death penalty in all the 50 states. So we know what the murder rates were in 1971, and we know what they were in 1973, and in between, the Supreme Court got rid of the death penalty, and we can see. So the argument goes that if the death penalty was a deterrent, then perhaps the murder rates increased. And we can check the murder rates in 1971 and the murder rates in 1973 and see if there's an increase or a decrease, or if it stayed about the same. that's the question that we're asking. Now, I want to say straight up front that I'm not a criminology expert. And there are two sides to this debate, and there are people who raise valid concerns about the death penalty and want it abolished, and there are people who say that we need the death penalty. And I don't intend to get in that debate, but this is an interesting debate that still goes on today, and we can address it with our matched pairs t-test. So you see this matching by state, and notice that they're getting the murder rates for 1970 year, and notice that they're sorting by states. Again, there's going to be a matched pairs approach, so that dot sort is going to be a feature a lot of times when we're creating these arrays. Notice that we are creating an array. So we have an array for 1971 murder rates sorted by state, and an array for murder rates from 1973. Now, notice the order these go in. They do not go in chronological order. We're doing this t-test rel underscore rel, and we're doing post comma pre. Right? Again, it's just making sure that the gain scores are calculated correctly. And when we run that, we get this rather sad news. The p-value is 0.00774, which is less than alpha. So if we jump over here, we can see that the t-scores are 2.778 and the p-value is 0.0077, which of course is less than 0.05. And by the way, 0.05 is our standard alpha. If we don't say anything about alpha early on in the problem, it's 0.05. Are there other appropriate alphas? Yes. We use 0.01 all the time. And yeah, are there reasons to change alpha from its standard value of 0.05? Yes, there are. But in this course, just assume that if they don't tell you, we're going to use a standard alpha of 0.05. And if the question specifies a different alpha, we can use that one. But for the moment, with alpha equals 0.05, p is less than alpha, and we reject the null. And this is actually quite interesting, because here, when we reject the null, evidence suggests that murder rates increased from 1971 to 1973. There was an increase. And again, in the middle is when the Supreme Court banned the death penalty. Now, this is what we have evidence for, that the murder rates increased from 1971 to 1973. What people are going to argue about is why that happened. And people who are pro-death penalty are going to say, well, it was a deterrent, and you take the deterrent away and the murder rates go up. And people who argue against the death penalty are going to attribute a number of different causes to why this happened. Again, it's not my job to debate what's the truth. We've just seen that we have scientific evidence that shows the murder rates increased starting in 1971 and then going to 1973. Okay, so the third example, if you look at the workbook, the notebook, we've got this. It's a survey that's done in a stats class, and I'm pretty sure that it's at North Georgia because there's a column for cadets, and that doesn't happen at a lot of places. As a matter of fact, there are only 6 senior military academies in the U.S., and I'm just guessing because I know the people involved. I'm guessing that this was a professor at North Georgia who did this survey. But one question he asked is, how old are your parents? All right, so we have a father's age and a mother's age given to us. And so the question is, are the ages of males and females in relationships different? Or are they about the same? And we know this happens in dating relationships that we're familiar with. People tend to date other people who are approximately the same age. Okay. And I have to admit that I got this part wrong. Sorry about that. We would like to use a not equal to. We're just asking, is there a difference? Now, the stereotype is that men are a year or two, a couple years, 3 years older than the women that they date. or that they marry, that's a stereotype, and we're going to see if that's true. I don't subscribe to stereotypes, but it is interesting to know if they're true. But we're just checking to see if this difference, if when we subtract the father's age minus the mother's age, if we get 0, which means there's no difference in ages, or if we get something different than 0. Okay? So let's take a look at the notebook. Sorry. Age example. There we go. So here is the survey, and like I said, everything else you might find at most other universities, but cadet is somewhat indicative of a senior military college. Okay, so look what they do. They go into the survey and they get the column mother age, and they go into the survey and get the column father age. So we have array. We're doing mother minus father. Okay, that means that if the fathers are older, right, then that difference will be negative. That's why I chose this one. Although I should have used a not equal to. Okay, and why don't we sort? Well, they're coming from the same table. All the values are coming from this survey table, and so they're already paired up based on whichever student answered the survey for that particular row. All right, so we run this, and we get a p-value that's about 3.96 times 10 to the negative 7th. So what do we know? We know that because it's 10 to the negative 7th, we know that p is almost equal to 0. That's a really small number. Is the p-value equal to 0? No. Is it really, 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 really close to 0? Yes. And so it's therefore less than alpha. It's less than 0.05. So we reject the null. All right, why? Because the p-value is the probability that the null is true. So remember that. That's a good time to stop and point this out. All right, what is the p-value? The p-value is an estimate that the null is true. What is that estimate? That estimate is essentially 0. We're saying that this could never happen. What's more likely to be true? That the fathers are older than the mothers in this particular research. Okay, so let me get rid of the marks there. And you can see they actually calculate the age difference. And there is approximately a 2-year age difference between the fathers and the mothers, and on average, the fathers are older. And then that's represented in this chart, right? Notice the 0 line. That's where the parents are the same age, exactly the same age, right? And oh, and then how did they do this age difference? I have to look at this. Sorry, oh, they did father minus mother. Okay. So then these portions of the graph above 0, where that difference is above 0, that's where the fathers are older. And the portion of the box plot here below 0, that's where the mothers are older. Okay, and you notice that 0 is about the 25th percentile, right? It's right there on the bottom of that rectangle for the box plot. So we have about 25% of the couples where the mother was older. And that means that we had about 75% of these couples and their kids reported that their dad was older. So if their kids happen to know their parents' age with any level of accuracy, then our result is valid. Okay, so what are we going to do to finish up going over a sandwich example? So we are trying, the setup for the sandwich example is that we're trying to open a sandwich chain in Dahlonega. And we're going to choose one of two franchises, either JJ's or Wirehouse. By the way, I think these are made up names. I don't think they're actually a JJ Sandwiches or a Wirehouse, although I didn't Google it. You can to see if there actually are any. I have never eaten or seen one of these restaurants, so I'm assuming they're made up. Um, so we purchase a sub from each of them, and then we have taste testers. Okay, and what are JJ? JJ are the ratings, is the array of ratings that the 10 raters gave to the JJ sub sandwich. Maybe it's not a sub, but a sandwich. And WH is the wirehouse sub and the 10 scores that the raters gave there. Okay, and then they're just creating a table showing the different scores. All right, and now notice, I'll just say that JJ was an array that had the rating scores, and WH was an array that had the rating scores. All right. So when they do the t-test underscore REL, right, it's a match pairs t-test. Why? Well, there are 10 raters, and each of them rated both restaurants. And a lot of times what they'll do in a situation like this is they'll take half of the people and they'll have the JJ sandwich first, and the other half of the people will have the Wirehouse sandwich first. Why do they do that? Well, there may be some bias that you induce by having 100% of the people of the raters taste one sandwich first and a different sandwich next. But anyway, these are the scores, and when we run it, notice that we do find a difference. The p-value is 0.0011, which is less than alpha. The question is, right now, we know there's a difference, but the question is, we still want to know which one's better, right? Which based on our data, which of these franchises we should consider opening. So notice they're doing WH minus JJ. So positive scores will relate to Wirehouse being better, and negative scores will relate to JJ being better. And Wirehouse wins, right? According to these raters, right, this is where they're seeing no difference between the sandwiches, where there's a zero difference, you know, but above this, remember that's Wirehouse. Positive scores are for Wirehouse. Negative scores are going to be for JJ. And so definitely we would reject the null. And when we check on which average score was higher, we find that our raters prefer Wirehouse, and that is probably um, the franchise we're going to contact when we want to open our own restaurant. We want the best tasting stuff. Now, notice that they can run this t-test independent, right? Just a straight up two sample t-test. But I want you to notice the difference, right? The p-values are very, very different. Okay, so if we just scroll up just slightly and get this p-value, the p-value that we got when we ran the matched pairs t-test was 0.0011. And now we're getting a p-value of 0.86. Why? Well, we ran the wrong test. Now this is an illustration, and and the point is that they don't just spit out the same thing. The two sample t-test is meant to be two independent samples, right? That's why they're talking about this. And the matched pairs, there is a dependence in the sample, right? It's the same people taking the pretest as they're taking the post-test. It's the same raters tasting the JJ sandwich as they're tasting the Wirehouse sandwich. So we call this dependent samples, and it doesn't match the p-value we get when we do independent samples. Independent samples is the wrong test, but it's really cool because when the data is paired, we actually have a more powerful test if we use the match pairs t-test. Now, in statistics, powerful just means better. Okay, so we have a better test if we use the match pairs design, and that's what this is. This example is getting at, and it's showing the box plots of JJ versus Wirehouse, and they're going through some calculations that you can take a look at if you're interested. But it turns out that the match pairs t-test is a one sample t-test that's operating on the gain scores, which is the differences between the measurements in the first sample and the second. Okay, and since they're matched up, we get rid of a lot of variance between subjects variance, and we're actually just measuring the difference caused by the thing that we're researching. So it turns out to be more powerful. And by the way, in the hypothesis testing link that's on our course calendar. Um, you don't have to, take your p-values and divide by 2. We actually have the code written out there for you where you can uncomment the one-tailed t-test and actually get the correct p-value on the first go. So this is a great research tool, and I'll be back soon. Have a great day.